Hi all. Yeah. So we were talking about the architecture, right? So let's high level recap. So what exactly happens when we, trigger any of the queries, right? So when we trigger any queries, like I'll just give you a high level overview what exactly it happens. Let's say, so the query life cycle, let's say you are executing some query, right? So I just mentioned here a select statement. You can consider it can be anything, right? So it can be any query, either select, insert, update, delete, whatever queries that we are executing. Okay, so let's consider we are executing a query here, right? Then it go for, sorry, query parsing, right? Query parsing is nothing but it validates whether the syntax of the query is correct or not. So the syntax, the keywords which SQL can understand whether those syntax is correct or not, right? If you use some FRM instead of FROM, so this is one of the keyword, right? So let's say join. So you are using inner join. So that is also one keyword. Suppose if you change anything, right? So after where clause you are using, after order by you are using where. So that is also a syntactical issue because there should be some order that you'll have to provide so that SQL would be able to understand the, so keywords that we are passing. Okay, so it will validate whether the syntax is correct or not. So once this is parts, once this is validated, then it checks the query binding. So binding is nothing but algebraizer, right? So yesterday I was talking about the schema binding. So person.person is a different table altogether, and if you don't specify a person as a schema and if you just execute a person, so it will be a different schema. So what I mean, like here you have that product, and if I use only product without production, so it's a different table altogether. So it will validate this table is bound to which schema, right? So then it start, so building a plan, it start building a query tree, right? So then once this is by the query binding is completed, then it it creates a query tree. So query tree is nothing but normalizing the query, right? So it will pass this to the next optimizer, and before it passing to the optimizer, it will just create a query tree. Query tree is just a normalization of the query. It understand what tables that we have, what are all columns we have, and what is the, so join, whether any joins are there or not, and any where clause, order by. So this will divide this entire query into small pieces, right? So that it will be easy for optimization, and it creates a query tree and send it to the query optimizer. So query optimizer work is to check the query and generate a plan, right? So check the query and generate an optimal plan. So optimal plan as in like it internally it checks like thousands of plans, right? So it is just it has some so calculation, and it keeps on checking that which is the plan which is sufficient to execute the query in a better way, right? So sufficient as in it will not keep on checking for a good plan, right? So it might be thinking that at this point, so the query might go for better execution, then it will stop and generate a plan, right? Before even it generates a plan, it checks whether the existing plan is available in the plan cache, that is in the memory or not, right? If the plan is not available, then it will go ahead and check further checks, right? So it checks that whether the simplification, yes, I I cannot hear you if you're talking. Just put on mute. You raised a hand. Uh, any questions? Okay. Right. So it will go to the optimization. So then optimizer, it will check whether the plan is simple, right? So whether the plan is simple or it is a complex plan. If it is a simple plan, it terminates and consider it as a trivial plan, right? It generates a trivial execution plan and terminates the further optimization checks. If it is not a trivial, right, it is a complex query, then it will go for further checks, right? So it checks like, so it performs some other internal searches, right? So it checks whether the index is utilized, whether we can utilize any of the indexes or statistics that we have, or even it go for parallel execution, right? So we know, right, parallel, if you run a query parallelly, that will run on multiple CPUs. We will talk that later, but it validates, the optimizer validates the cost of the query, and based on that, it will consider whether it should go for parallel execution or not. Okay, so to answer your question, if the SQL Server reboots, the whatever available in the memory, that will be removed, that will be flushed out. You will not have that, say the plans or data cache. So whatever available in the memory, everything will be um, removed. So again, it will go for compilation and then generate a plan if the plan is not available in the memory. Yeah, so it is very difficult to SQL Server. Yeah, if SQL Server restarts, then that is the reason we should not restart frequently, right? So if we restart for any planned activities for patching, as an example, so definitely you will have to restart, and the plans, data pages, everything will be fleshed out. And if you have a proper, or if you have a, speed IO or storage, then the pages will be scanned from the data disk, and then it will be copied to the memory data cache. And whatever plans that we have, so optimizer is fast enough, right? So within few seconds, the plans will be generated for the query. So definitely that also impacting, if the plan has to be generated, compiled and all. But yeah, we cannot do much, right, if the plans are removed from the plan cache. Right, so we cannot do anything. So the optimizer will take care of compiling the query and cache the plans. Good. So it will validate the simplification of the query and generates as a trivial plan, and it checks whether the statistics are up to date, or so whether the table has the indexes and where indexes can be utilized or not. And it perform different searches, right? N number of searches, I would say. It is not simple, simple process of generating a plan. It checks N number of searches internally to find a optimal plan for the query, right? See here, the goal of the query optimizer is not to find best execution plan. Let's say, for example, to generate a plan for this query, optimizer took 1 second. Optimal plan, right? It is executing in 10 milliseconds, right? So there might be some other, so plan or other search where it can execute only 5 seconds, 5 milliseconds, or even it is more than 10 milliseconds, right? If this optimizer keeps checking, it took around 2 seconds, 2 milliseconds to find the plan. So if it keeps checking for a good or best execution plan, then it has to spend more time to find the optimal plan. Then next plan can be less than 10 seconds or more than 10 seconds, that we don't know, right? So instead of spending more time on compilation and generating a plan, the optimizer will identify a proper or the optimal plan for the query, and it will terminate and go for optimization and go for so compilation and execute the plan, right? That is what the query lifecycle. Once the query is optimized, then it will go for query executor, and query executor will execute the query and send it to the storage engine because it needs some data through a OLEDB connector. So it connects to the access method, and access method is a communication channel within the storage engine, right? So if you want to do any of the operations, let's say for example you are modifying some data, and storage engine will pass that information to the transaction manager, and the storage access method will pass that information to the buffer manager parallelly, right? So transaction manager to write the data into the transaction log file, write the transaction information into the transaction log file, and buffer manager to write the data into the data data pages, right? So this is if it is select or update. So then access method, then it will be sent to the buffer manager, and buffer manager will check whether the page is available in the memory so that it can be modified that page here itself, or it can get the data from the existing page itself. If the place is not available, then it will connect to the data file and get the page and keep it in the memory, that is in your data cache. Once the page is available in the data cache, then the data will be retrieved and send it to the access method, and from access method we will send it back to the relational engine and to the client. If it is any modification, then from access method it will be sent to the transaction manager, and transaction manager you'll have that log manager and log manager, and log manager it will be writing into the transaction log file. Before writing into the transaction log file, you'll have a log cache in the memory itself, right? So every transaction, every single transaction we will not write into the transaction log file. Before writing into the transaction log file, you will have a log cache. Okay, log cache, it will be writing into the log cache in the memory, right? So in the memory, as soon as the log cache, that is your I think 64 by 64 KB, for example, and as soon as this log cache is full, then the entire cache log cache will be sent to the transaction log file, and transaction log file hardening happens. Hardening is nothing but writing into the transactional log file. So it will harden into the transaction log file. If not full, and if the transaction is committed, let's say 8 KB, the transaction is committed with respect to whether the transaction, whether the so the log cache is full or not, it will keep writing into the transaction log file. If the transaction is completed, then it will write into the transaction log file. Or if the checkpoint happens, whether the transaction is completed, whether so it is an 8 KB, whatever it is, whether the transaction is completed or whether the log cache is full, if checkpoint happens, that also write into the transaction log file. Whatever data which is there in the log cache, it will write into the transaction log file. That is what we call it as hardening of the transactions, right? And write ahead logging, basically. So write ahead logging is nothing but writing into the transaction log file before even writing into the data file, right? So the page will be updated, and as soon as the checkpoint occurs, checkpoint does two things. One, it will write the pending transaction logs from the log cache into the transaction log file. That is one thing. And second thing, it will validate whatever pages which are there in the data cache. So whatever pages which are there in the data cache, and it will be flushing these pages to the data file and marking that checkpoint LSN information to the transactional log file, and checkpoint LSN information also writing into the database. So we have some internal pages, so that information also will be written to the database boot page. That is the main so system page. It will write into the database boot page so that it will understand when the last checkpoint happens during the database recovery. So whenever database is restarted or whenever the database is crash recovery happens, then it will understand that this is my checkpoint LSN, so that I'll have to start my recovery from this point, right? So it will scan through the log file and understand and perform the recovery phases that we have, right? This is the simplest example for update and select statement. Okay. Um, and as I mentioned earlier, the checkpoint is help to move the pages. That is your copy. It will move. It will not remove the pages from the data cache. It will just copy the pages and flush it to the data file, right? So it will just flush it to the data file so that it will mark as a clean, right? Those will be marked as a clean and it will be flushed to the data file, and the page still be available in the data cache, so that you are executing any select or even if you are doing any modifications, it no need to perform any of the IO from the storage. IO to or from the storage to avoid any IO operations. We are caching the page in the memory. So whenever you do a select, so it will be picking from the memory itself, or updates, it will be taking the page from the memory itself. So if there is any memory pressure, let's say for example, you need a few other pages to be placed in the memory, right? So if that is the case, we have some other internal process, we call it as a lazy writer. It checks what is the memory utilization, and based on that it will start invoking and keeps, so flushing the pages from the memory to disk. It will remove both clean and dirty pages, both, right? If there is a clean pages or dirty pages, it has internal calculation and whatever least recently used algorithm, and it will send or move those pages to the disk data file. What might be the issue? Buffer cache hit ratio. We'll talk that so more in detail in the memory. So buffer cache hit ratio is nothing but what is the percentage that a page, what is the percentage that we are so hitting the page which is there in the memory. If that is less, then in that case the pages are not available in the memory, that is keep flushing into the data file. So we'll have to check if there is any memory pressure or any other issues on the server itself. Okay, so this is what we discussed yesterday, and query life cycle. So if you have any questions, just let me know. Otherwise, we'll go for so user mode scheduler, that is the SQL operating system that we have. Okay. So this one, right? So I said, so we will just execute the queries and all and net libraries, and we'll execute the queries. So while executing the queries, so whenever we execute a queries, so where the query will be executed or how the query will be executed, right? So we will have to have a CPU to execute the query, right? So every query that we trigger, it has to run on the CPU to process, right? So if you see that any queries or anything you perform, it all depends on the operating system and CPU, right? We will talk that user mode scheduler, how the scheduler works and how the threads will how so the work got the queries will be executed. So queries will be executed by whom, right? So we will talk that. SQL operating system, earlier we used call as user mode scheduler. So what does it mean by user mode scheduler? Let's say you have a SQL server here and you have an operating system here. So SQL server resides on the operating system. Let's say you have multiple CPUs on the couple of CPUs, right? So let's consider the two CPU cores that we have, CPUs we have, right? So I was talking, right? Whenever you perform any operations, it needs CPU to run that particular query, right? So you need CPU to run that query. So the query will be executed only on the CPU with the help of other resources like memory, storage, everything with, so it helps to improve the performance of your execution. But the main thing is the CPU that it has to execute, right? So earlier, I think before even 2000 version, so let's say the queries that we have, the SQL server, let's say I have 10 queries I want to execute, right? If we wanted to execute 10 queries, then 10 queries will be sent to the operating system, right? So these 10 queries will be sent to the operating system for execution, right? How the 10 queries will be sent to the operating system? This with the help of threads. Okay, so normally whatever queries that we are executing, that queries will not execute. So the smallest unit for execution is your thread. Thread is nothing but a smallest unit of execution of your query. I should have that just a moment. Okay, so let's say this is your process. Okay, so this your this your computer, this your whole computer system, and whatever we have it here, so whatever applications that I have it here on the system, so each application we call it as one process. So each application we call it as a single process, right? So if it is a notepad is another process. If it is a PowerShell is another process. Whatever application that we have in the operating system, so that we call it as a process, right? Each process will create some task to execute, but the process will not execute itself, right? Process should have something to execute. The process will create, let's say for example, SQL server will create 10 tasks, select, insert, update, delete, whatever it is, it creates 10 tasks. If it creates 10 tasks, then those 10 should be executed by some so worker, right? So it will be creating, and that will be executed by a worker. That worker is called as a thread in SQL server world, right? So here if you see, the process is an execution unit. It's just a container for executing the task that we have. Task is nothing but any work that we are triggering into the SQL server to execute, right? Process is an execution unit which has the multiple tasks, whereas some worker has to take care, right? Some worker has to take care, some threads has to, some execution unit has to take care to execute this task, right? What are those execution, so context of executing these tasks are the threads. Threads is nothing but it is just a smallest unit of executing your task, right? It will execute, it will take the task and execute on the CPU and give the result set, right? So thread is as a thread process does not execute or run threads associated with the, or run threads associated with the process run on processor, right? So whatever which are running on the processor, right? So CPU we call it as a processor on the on the operating system. So we have one CPU here, we have another CPU here, right? So these two we call it as a processors. Okay, so this is process. Individual CPUs we call it as a processors. Whatever we generate or execute on the on the SQL server, it will go ahead and execute on the individual processors, right? So if you have 10 tasks created or 10 so works created, those 10 tasks will be picking up by the individual threads, right? So thread is the smallest execution unit, so which execute your task. and this pick up this thread, this task, and will go ahead and execute on the processors, right? That is the behavior of your thread execution. Now let's say you have a SQL server, and SQL server operating system, and you have two CPUs, and if we create a 10 threads here, right? So earlier what happened, all 10 threads exposed to the CPU, right? All 10 threads, I mean, it is picking up by the threads, 10 tasks, and 10 threads will be exposed to the CPU and start executing on the CPU itself, right? So what does it mean? It will expose all 10 threads. Then we have a two CPUs. At any point of time, only one thread can execute on the CPU, right? So multiple threads cannot execute and do some multiple tasks, right? One thread can execute on one CPU, and if it is come out of the CPU, then another thread will go ahead and execute. So now I have two CPUs, then the thread will be distributed as 5 threads here on the CPU and 5 threads here on the CPU. And there is no guarantee that it will be 5. So it can be anything, because this is the operating system level. So we don't know, the operating system doesn't know which thread to be, whether it has to split across or not, right? It can go for 10 threads here and 0 threads here, or 4 threads or 6 threads. There is the imbalancing while spreading the threads across, spawning the threads across, right? So let's say these 10 tasks are waiting in the operating system queue. Then what will happen? One thread executes on the CPU. Then there is a term called as context. There is a term called as quantum. All right, quantum in the operating system level, the value is defined as 4 milliseconds. What does it mean by quantum? So as soon as the thread is completed its execution, it will come out of the CPU, right? It will come out of the CPU. The thread will come out of the CPU and and it will allow other thread to execute on the CPU. So what does it mean? I have 5 threads outside, 5 threads waiting on the CPU. Then one thread is executing here. Then after 4 milliseconds, it will come out of the CPU and it will be awaiting in the operating system itself. Then it will go to the next thread. The next thread will come back after 4 milliseconds. It will come out of the CPU. Then it will go ahead and execute the next thread, right? Likewise, you will have multiple contexts, multiple yieldings. So this we call it as a thread yielding, right? So yielding is nothing but it will come out of the CPU and then it will allow other thread to execute on the CPU, right? So what will happen once it is 4 milliseconds is completed? Then it must have done some work. It must have done some work in the 4 milliseconds. It can be anything, right? 4 milliseconds. Then this work will be written to some pointers. So this work will be written to somewhere, right? So that it will understand that this is completed 10%, and during next execution, next turn, it will pick up from that particular 10% and proceed with the further execution. You will have a more context switches, right? Context switch is nothing but the context of the current execution will be written to the some other so pointers or place where it will be picking up that value during the next execution and start processing the queries, right? So you will have a high context switches because the threads are available here in the queue, and after every 4 milliseconds, the thread has to yield from the CPU and will allow other thread to execute on the CPU, right? So if you are doing that, so then you are doing high number of context switches and high number of yields, right? So we are doing so many yields because we have 5 threads. Let's take, I have 100 queries executing, then everything will be spawned and 50 threads waiting and 50 threads waiting on another CPU. I'm just taking 2 CPUs. Let's consider that whatever CPUs it is. and waiting, and every context, right? Every 4 milliseconds, the thread will come out of CPU and will allow other thread to execute. Then what will happen? The 50 threads, the first thread will execute and will come out of CPU. Then this thread will be in the end of the queue, right? So the queue is like 1 2 3 4 5 till 50, and if first thread executes and come out of CPU, then it will be at the end of the queue, so that it will wait for its turn to execute the thread, right? So if that is the case, it is so much time, wait time, and so many contexts that we will have to perform to execute the query, and it will cause the high CPU, and you will have a high context switches and all. So to this is the behavior before even we have a user mode scheduler. This scheduling is only the operating system level scheduling, because we are spawning, we are just creating 100 threads, we are spawning, or we are just giving all these 100 threads on the CPU, so that it will take care on its own time, that is your 4 milliseconds, and come out of CPU, and go ahead, it will allow other threads to run on the CPU, right? So if we are spawning all the threads and allow operating system to schedule those threads to run on the CPU, then you will see a performance issues, because we are doing so many context switches, right? Coming out of CPU, and so we'll allow other threads to run. Everything is so huge CPU cycles and wait time. The 50 threads, right? So each thread just perform 4 milliseconds, it has to wait 50 into 4, the total wait time of all the threads, or 50 thread has to wait for this long, okay, 200 milliseconds or whatever, like it has to wait for it turn to come and execute on the CPU. So you will have a huge wait time to get its turn to execute on the CPU. And let's say you have a high priority thread comes in, right? So this all running on the operating system level.
Excuse me.
Yep.
Before you go further. So it's me, let's say we have 10 query we want to run at the same time on the server. So the 10 query, you say they're going to share the 2 CPU that is on the server, right?
Mhm.
So cool. Now you said each query will wait for 4 milliseconds.
Mhm.
Does it matter whether that query successful or not?
No, that's what, right? So doesn't matter whether the query is completed within 4 milliseconds or not. As soon as it meets that quantum, that is 4 milliseconds, it will come out of the CPU and it will be in the queue in the operating system.
So
Mm,
if the query is not completed
mm.
and it is already 4 milliseconds by counter, is that by default or by what you set on it?
Actually, I have not completed. This is the operating system level when you don't have a UMS, user mode scheduler. So currently this was way before even 2000 or 2005. So when we don't have a user mode scheduler, so we have introduced something called SQL operating system that will help you to execute your queries, to answer your queries. The query is not completed and it's quantum 4 milliseconds, it will come out of the CPU, it will be waiting in the CPU itself. It will not go back and give that confirmation to the SQL server. It will be in the SQL operating system stating that I have this 10% or 15%, so that it will write into the context, that context of the thread it will write. And whenever it gets it turned again, because it has just completed 15%, then it again executes on the CPU, and remaining percentage will start executing from the point where it left that context, where it left that execution. So let's say, for example, we processed only 10 rows, I have 100, then it will start executing from here, and it will process further, and as soon as it reaches that 4 milliseconds as a quantum, then it will come out of CPU and will be waiting on the CPU to be available. That is a 4 milliseconds when there is no UMS involved. But current like SQL Server, what we are working, that are all UMS. So SQL Server will take care. I'll talk in a bit.
Okay. Okay.
Now, so it is a understanding UMS you don't have, user mode scheduler or SQL operating system we don't have. So I have a Windows operating system, and it is taking care of the scheduling of our threads, scheduling of our process, SQL Server task. Thanks. Good question. And if you have any questions, please, maybe I will not monitor that raising your hand or not. So just speak out, and so that I will try to explain. Okay, cool. So this is the Windows operating system. So you will have high number of contexts and high number of wait types, because you are just coming out of CPU within 4 milliseconds. Every 4 milliseconds, you are coming out of CPU, and the thread or the query might not be completed. It has to wait in the operating system to get its turn to execute again and process further work. Then it will be a delay to the user as well, right? So because they have to wait for this thread to complete. So then, so what else the problems with this thread? Let's say, for example, this is spawning to the Windows operating system, right? Let's say some other thread comes in. Let's say this is operating system is for all the process, not only for SQL Server, right? So operating system is for all the process. You can have SQL, you can have Notepad, you can have PowerShell, you can have, so any other like this Zoom also one process, right? It also requires some threads to execute on the CPU. So it also needs some threads to execute on the CPU to process its work. Or notepad.exe, that also an executable, a process which is on the CPU, right? So for example, perform, so that I can show you that what are all process that we have, right? So perform, where we can see we have something called process object. This is process, this is processor. Processor is nothing but your operating system, the CPUs that we have, that is what we call it as a processor, right? So I have 4 CPUs, I have 0 to 3, right? Processors, right? CPU, whatever the counters it is. Process is nothing but whatever applications that we have on the server, right? If I take process, right, these are all applications that I have, right? If you see that Zoom, whatever, like, so I have on this, so I have everything on this. Like if you see so if I open a notepad, and if I select whatever process it is, right? So it also create one executable, right? So notepad, whatever it is, like if you see the SQL Server, SQL agent is one process, and SQL agent, so I have multiple SQL instances, and SQL Server, I have 3 processes created because I have 3 instances of SQL Server installed on this, right? Each process is nothing but one application we have on the computer installed or running on the computer, right? So this is basically whatever process which are currently running. If I stop the SQL service, this if I stop only 2 SQL services, then you will see only one SQL Server process here, right? So that is what it is. Like it doesn't matter if only with respect to only that is a SQL or not. So you will have the threads created and execute on the CPU. So what I mean, sorry. What I mean, you have a SQL Server, you have an operating system, you have CPUs, and this waiting threads can be from any other process also. Let's say, for example, I have a some other application that I have, like let's say Notepad, and it creates 2 threads. Let's say, so I have 50 threads here, 50 threads here, the SQL threads, and I have other threads also will be in the same queue or will be in the line, because the Windows doesn't know, or Windows even it doesn't bother whether it is a SQL threads or it is a notepad, whatever it is, because I have a threads and I have to execute on the CPU. That's it. So it will be in the queue and it will start executing one by one. In between, it can execute the thread for notepad also. Can be, right? So after 4 milliseconds, it will allow other thread to execute. The thread can be any other application also. Now, if that is the case, if you have high number of process, so like multiple applications, then you will have keep so piling up this queue and start executing within 4 milliseconds and it will come out of CPU, right? So you will have a high context switches. If you have a high context switches, you will see a high CPU utilization by the Windows operating system, the kernel level. So we'll talk that later, kernel and user mode. So this is a user mode and this is a kernel mode. So kernel level, you will see that high CPU utilization because the thread which is in the CPU, which is in the operating system, will keep coming out yielding within 4 milliseconds, yielding once it is reached 4 milliseconds, right? So you will have that context switching issues. Second thing, let's say high priority thread, right? Some Windows operating system thread or some internal thread which needs a priority, right? Which has a higher priority than the threads which we have. So SQL threads all will have the same priority. The priority is 7. If you are not sure that priority, and we can see that cell sp underscore read error log. So SQL Server is starting at normal priority base equal to 7, right? So this is a range where, so SQL Server or any application, any process that we have, it will take care. So all threads which is in the SQL Server is at a priority level 7. So all at the same priority. So you will not have high priority or low priority threads, right? So it will have all same priority. But let's say if it has some other priority threads, right? So from the Windows or background thread, it executes, then with respect to whether the quantum is completed or not, that is your quantum is 4 milliseconds. If the thread is executing for 2 milliseconds, if a high priority thread comes in, then this thread will be removed or yielded from the operating system CPU, from the CPU. Then it will allow other priority thread to execute on the CPU, right? So this is the problem when we don't have a operating SQL operating system. So SQL operating system, you will have if you don't have a SQL operating system, the Windows will schedule the threads. Windows is a priority driven. First thing, priority driven, as in if you have a high priority threads, the thread will be so yielded from the CPU and it will allow other priority thread to execute on the CPU, right? And the preemptive is nothing but 4 milliseconds. Preemptive is nothing but the yielding from the CPU before even completing its execution. So 4 milliseconds, it will preempt from the CPU or yield from the CPU and execute, allow other threads to execute. So it is a preemptive mechanism, the Windows operating system, right? So you will have a high CPU bound because all threads are waiting at the CPU on the operating system itself, right? And then you will have a slow execution because the thread is not completed. If the thread is not completed or the task execution is not completed, but still you are waiting on the Windows operating system. So you will see performance issues with the SQL Server. So Microsoft developer team or Microsoft SQL operating system development team, so they so came with the solution. So they thought, so why should I allow SQL Server to schedule the threads by the operating system? So why operating system schedule our threads, right? So instead of that, why don't we schedule our own threads by SQL Server process itself, right? So that is where the SQL operating system came into the picture. Let me tell you how that works. This is all almost like talk, but yeah. So scheduling like so this is a preemptive, so non-preemptive scheduling. Yep. So SQL Server, we call it as a non-preemptive. So with respect to whatever so thread priority that we have, it will not be removed from the CPU. But yeah, so we will talk that this is a preemptive and this is a non-preemptive. So what does it mean? So Windows uses a priority driven. I was talking, right? Priority. If the priority thread comes in, then that priority thread will go ahead and execute on the CPU, whereas the executing thread, current thread which is executing, will be removed. I mean, will be yielded from the CPU, and it will allow other high priority thread to run on the CPU, right? Preemptive scheduling algorithm, thread execution within their quantum, right? So this is the operating system. So threads execute within their quantum, that is your 4 milliseconds quantum. Once the quantum expires, threads are scheduled off. It's nothing but it will come out of CPU and must wait for to schedule them again. And it is nothing but your Windows operating system. So the operating system of CPU, it will allow other threads to execute, right? So it will come out of CPU and it will write a context of the thread, and it will wait for that next turn to execute on the CPU, right? It will wait all threads complete its 4 millisecond quantum so that it will start executing again. Potential for thread to be preempted before quantum expires by high priority threads. That's what I was talking, right? If there any background thread, or if there is any system thread, or if there is any high priority thread comes in, then the thread which is currently executing, let's say SQL thread currently executing, which is a priority of 7. If the thread is currently executing on the CPU, then the thread will come out of CPU, right? And it will allow other high priority thread to execute on the CPU. These are all kind of drawbacks, right? So because why SQL thread will come out of CPU to allow other threads, right? So we have to maintain our own scheduling instead of giving to the operating system. So that can be done. Right? Then Microsoft development team has introduced a concept or scheduling mechanism called UMS. So this is user mode scheduling. So what it is telling, so I will schedule my own threads rather than allowing Windows to execute the threads, Windows to schedule the threads, right? The main design goal of UMS is so you can consider smart about when it pays. Okay, let me show you here. You have a SQL Server process, you have a operating system, you have an operating system or Windows operating system, whatever, right? We have a multiple CPUs. So now in that we have a layer called UMS, user mode scheduler, UMS, or SQL OS, right? SQL operating system. Now what will happen? I have 10 queries or 10 queries or 10 tasks. And I was talking, right? Each task will be assigned to one or more threads, but let's consider that we are assigning each task one thread to perform its work. Now I will be creating 10 threads. Right? So I will be creating 10 threads. Now, what SQL operating system does, SQL logically it creates some schedulers. Logically, it creates some logical schedulers. This is scheduler 1. This is scheduler 2. So this scheduler is based on the number of CPUs that I have. If I have only 2 CPUs, then SQL Server will logically creates 2 schedulers, and it will bind this scheduler to this CPU. This will bind this scheduler to this CPU, the operating system level. So there is a mapping, one-to-one mapping, whereas scheduler 1 is mapping to CPU 1. Scheduler 2 is mapping to CPU 2, right? So it will logically create a scheduler because it has to have that its own scheduling mechanism, right? Then it has to have a own container kind of thing. You can consider that scheduler is nothing but a container, logical container, whereas individual CPUs are a physical containers where we execute the CPUs, where we execute the threads. Now I have a scheduler 1 and I have a scheduler 2 based on the number of CPUs that I have. Now each scheduler, this thread will be evenly distributed across both the schedulers. What I mean, evenly distributed in a round robin fashion, right? So for example, one thread is assigned here, another second thread is assigned here, third one, fourth one. So evenly in a round robin fashion, it will assign a threads here. Let's say it created 5 threads, it assigned 5 threads, it assigned 5 threads. So in the SQL Server scheduler, we will have that 5 threads now. In the SQL Server process or scheduler 2, I have a 5 threads here. Earlier, when there is no UMS, all 5 threads will be assigned or spawned to this CPU. All these 5 threads assigned or spawned to this CPU. Now, what SQL operating system will do, it will not spawn or it will not allow all the threads, or it will not schedule all the threads to spawn on the CPU. What it will do, it will take one thread at any point of time. It will take one thread, it will send to the SQL operating system to execute its work, right? What it does, it will have the scheduler queue. From the queue, it will send only one thread at any point of time. So instead of sending all the threads, it will send one thread. First thread, it will send to the SQL operating from SQL operating system to the Windows operating system. It will send one thread. So at the same time, the scheduler 2, it will send another thread. So it will send another thread. That is your first thread in the scheduler 2. It will send to the CPU, and the remaining threads will be waiting on the CPU on the SQL scheduler itself. So, right, we are not spawning to the Windows operating system CPUs. The physical CPUs we are not spawning. So we are just keeping the remaining tasks or threads in the SQL Server operating system level. This SQL Server user process only we are keeping the threads. So we are sending only one thread. The thread will go ahead and execute on the CPU. So it will not, the thread still the, so the what we call quantum is still applies to the Windows operating system level, right? So this, till this point, the quantum applies. If the only one thread is spawning, the thread is executing here, it will check if there is any other pending queue on the CPU. That is your operating system level CPU, if there is any other pending threads. If we have only one thread, so because we are not spawning all threads at the CPU level, we have only one thread running on the CPU, then it's continue its execution without, so yielding from the CPU, it's continue its execution of the thread, right? So as soon as this thread is completed, so I will tell you when this thread come out of CPU, but yeah, as soon as the thread is completed, its execution, it will be send it back to the SQL Server operating system, so that it will allow other thread to execute on the CPU. So as soon as this thread is completed its execution, then next thread, which is in the queue, will be exposed or will be scheduled to run on the CPU. So SQL will allow one thread to run on the CPU at any point of time. When this thread will go ahead and so go out of this SQL operating system and go back to the SQL process, there are certain conditions. One, thread completes its execution. So if the thread is completed its execution, then it will go ahead and it will come out of CPU and will go back to the SQL process. Or if the thread requires some resources, let's say lock or page, whatever, or anything requires some memory to be available. If it needs to wait for any of the resources, then it cannot keep waiting on the CPU, right? It has to come out of CPU and go back to the scheduler and wait in the scheduler queue. I will talk what are all queues that we have in the SQL schedulers. But for now, understand if it needs to wait on some resources, then the wait cannot be on the CPU, right? It will come out of the CPU and it will go back to the SQL process. Third, if so, like for example, let's say the thread is not completing, we are not allowed the thread to run continuously, so some whatever time, right? So Microsoft developer, they have written in the code, that is SQL Server.exe code, they mention some yield points. Right? So yield points, for example, a thread meets this yield point, right? Whatever thread is executing continuously, if that is the case, the thread might never come out of CPU. It will keep on executing on the CPU itself, right? So that is a problem, because if it is keep on executing on the CPU, it will not allow any other threads to execute. That is the reason Microsoft developers mention some yield points in the code, that is SQL Server.exe code, some yield points. If this thread, the executing thread, if it meets any of the yield points, then it will come out of the CPU and go back to the SQL process, right? So these are the main triggering points which it comes out of the CPU and go back to the SQL process. If the thread execution is completed, if so if it needs some resources and it has to wait for the resources, it cannot be running on the CPU, then it has to wait, it has some yield points, so that we will not allow the thread to keep executing on the CPU. We will see if it meets the yield point, so that it will come out of CPU, right? These are the three main triggering points which it comes out of the CPU. Okay, 1 second.
I have a question.
Sure. Yeah.
So do we still have the quantum time, like the what's that, 3 millisecond? Was that the right number? Do we still have that?
4 milliseconds.
Because you say the thread has to complete, right?
4
Yeah,
milliseconds
4 millisecond, right?
is still there. That is at the operating system. So what I mean, for example, let's say we are spawning only one thread, right, from SQL Server. So we are just spawning only one thread, and the thread will execute, and it checks as soon as it reaches 4 milliseconds. It checks whether if there are any other threads in the Windows operating system level. If any threads available here, if any threads will available, then it definitely come out of CPU and it will allow other threads to run.
Okay.
This situation happens because we are not spawning multiple threads from SQL to
Right.
Windows operating system, right? We will not have SQL threads, but there are chances that we have other process on the same server. Let's say Notepad, it has one thread created, and currently
Right.
SQL thread is executing. It checks if any other threads in the queue. 4 milliseconds, it will come out of CPU and will wait on the Windows operating system queue itself. It will not go back
Right.
to the SQL operating system. Then it will allow this Notepad thread to execute and so come out of CPU. 4
Okay.
milliseconds is still available. That is at the Windows operating system.
Okay, thank you.
Yeah. But the thread will not come out of so operating system and go back to the SQL process. No, so thread still be available on the Windows operating system, and as soon as it reaches that 4 milliseconds, it checks if any threads are available. Then if no threads available, it continues its execution.
Okay, so the UMS is basically to manage the traffic.
Manage the thread controlling. Yes, correct.
Thank you.
Sure. Right. So any questions? So I'll show you. Yeah.
So please go back to that diagram.
Okay.
So that means since we already introduced the UMS, so the query or the result or output that will go back to SQL Server will be the one that completed. Right? Or either of these three that you mentioned. Is that correct?
Correct.
So the one that is not completed, that is on Quantum, will be controlled by OS.
Correct.
Right? So is there any chances that, you said that the query will be coming one by one, not like, because we already introduced EMX now. The query, if we have 10 query, one at a time will come to the CPU, right? So is there any time that will be a traffic on this OS when the query is coming to get the CPU? Is there any time that will be a traffic in this CPU because we already introduced EMX? Is there any time that will be a traffic on the OS that will make the query to stay more than 4 milliseconds?
So at the operating system level, you're talking?
Yes.
Yeah, that's what, right? Like, so 4 milliseconds, I was just explaining, right? 4 milliseconds is still at the Windows operating system level, and we are sending only one thread at any point of time. So I would say, like, so instead of query, so I'll mention the threads, and one thread will spawn at a time. And if any other process that we have on the system that doesn't have a UMS is only dedicated for SQL Server, that will not, that doesn't know like how to schedule the threads and all. So if any other process that we have on the Windows operating system, that threads will be spawning on the Windows scheduler, Windows processor, that is your Windows CPUs, and it will be in the queue. Let's say, for example, you have a SSRS. It doesn't know, like, so UMS and scheduling and all. SSAS, analysis service, and it requires some task to be completed, and it spawn like multiple threads. If that is the case, these threads also will be waiting on the CPU. Let's say, for example, 10 threads and one SQL threads. Then this SQL thread is executing on the CPU, and it will come out of that CPU after 4 milliseconds. Then it will allow the SSRS or SSAS threads to execute on the CPU. So that quantum is still available. That is the reason we always recommend to have a dedicated for SQL Server. If you have any process which is installed along with the SQL, that will see some other performance issues, like one of this is the CPU. The query execution would be late if you have a multiple threads waiting on the CPU itself. So the 4 milliseconds is still valid.
Okay, so that means if you have like 10 query waiting on this CPU, and we have one SQL query waiting on the CPU too. So this OS does not care whether it is SQL query or OS processor. It's go after 4 milliseconds. Each query that is executing will leaving the CPU for another query.
Correct.
So where will this query that live for 4 milliseconds, where is it going to be?
After 4 milliseconds or during the 4 milliseconds?
Yes, where is it going to be? Where that query will be? Because the query is not completed before 4 milliseconds. Where the query will be?
No, so query is logical, right? So query, whatever task that we have, that is a logical. So logical, you will have that at the SQL server, and the thread, that the thread will go ahead and execute on the CPU. The thread will be executing on the CPU, and as soon as it reaches that 4 milliseconds, we have some internal queue. Let's say, for example, I will talk that in a bit, SQL queues, but at the same time, the Windows level also, we have some queue. Let's say, for example, it is a runnable queue, just an example. So it will be in the thread will be placed in the runnable queue.
Okay, got it.
Okay, so in the runnable queue, and next, once the thread is completed, let's say, for example, this thread is currently executing, and after 4 milliseconds, it will be at the end of runnable queue. And next thread will go ahead and execute. So likewise, it will be in the queue on its own.
So it will not be that particular query that is already on runnable, that thread that is on runnable. Each
Yes,
thread will be run according to first come first serve.
it
You
will be
get my point?
uh,
It will run according to how they queue. You know, we may have like five trends
Hmm.
at the runnable stage.
Hmm.
So they are going to run how they came to that queue.
Okay, so I will talk in a bit, like how that scheduling and all we come into the
Okay.
picture. Yeah, so I'll talk in detail, like whatever schedule, whatever queues that we have, right? So that you will understand in a better way. I will talk that how that threads will be go ahead and schedule, or so how that whatever threads which are there in the runnable, and how that understand and it has to run on the CPU. I will talk in a bit.
Well, quick question before we proceed. I just want to ask, with all these processes now, assume if there is a conflict between them and there's no way forward for the thread that is on queue to go out to run or to execute. Is that the reason for like an error called non-yielding scheduler error? Does it have anything to do with that?
Yes, your good point, right? So if the thread is keep on running on the CPU, if it is not yielded from the CPU, whatever, so it's keep on running. And if it is not yielded, so that is where we see that non-yielding errors or non-yielding scheduler dumps, right? That is what we mentioned here as a yield point. For example, if you see that non-yielding scheduler, there are high chances that there are some high chances that there could be some bug at the SQL Server level itself, or some issue with the operating system performance, right? Because SQL Server defined that yield point. If it is not yielding, but whatever reason, so it is not properly defined that yield point. In that case, there must be some bug at the SQL level, or some performance issues at the Windows level, where it is keep so running on the CPU. Good point. Yeah, that is what we see here. Yield non-yielding so threads.
Thank you.
Good. Right, so any questions? Cool. So this is what I was talking. UMS is a cooperative user mode scheduling. I will talk in a bit what is that meant be. Uh, Simply put, UMS is a thread pool, right? So UMS is a thread pool where it schedule one thread at any point of time. Allow SQL to be smart about when it waits. Right, allow SQL Server management of CPU time, right? So it will allow only one thread, so that it will manage the time that it is spending on the CPU. Logical, not physical. We do not change the anti-scheduling, that is your Windows operating system scheduling behavior. We just manage it, right? That's what I was talking, right? If it is 4 milliseconds, that 4 millisecond will be available. We are managing how to schedule the threads. Right, so here if you see at the SQL Server, so I have 4 CPUs, right? I have sys.schedulers, sys.dem_os schedulers. This will tell like how many schedulers that I have, right? Visible online. So whatever offline, so that will be there. But if you see that visible online, these are the threads that these are the schedulers I will be, SQL will be creating logically, and mapping each scheduler to its own processor, right? So scheduling to its own processor. If you see here, scheduler ID and CPU ID, right? Scheduler 1 is mapped to CPU 1, scheduler 2 is mapped to 2, 3 is mapped to 3, right? So each scheduler is mapped to one CPU, right? So that whatever threads which are executing on 0th scheduler, it will not execute on CPU 3. It will be executing on individual the mapping, so exact CPU. Scheduler 1 is mapped to 0 CPU, so that whatever threads which are executing on 0 scheduler will be mapped to and execute on the CPU 0. Cool, right?
Hello,
So
Chandu.
yeah,
Chandu, this is Ayan.
yeah.
Yeah, Chandu, for example, if 3 to 4 users are selecting the performing any action, 3 to 4 users, so it will be used by 4 CPU.
So it doesn't matter, so whatever uses that the query is executing, right? So again, so even one query, one user connected and executing 4 queries, the 4 queries, each query will be will be spread, the 4 queries, and that will be created as a task, individual task, and the task will be assigned to a thread. So even one user executing four tasks, and each task will be assigned to one thread, so that 4 threads will be created. The 4 threads will be spawned across multiple CPUs. With respect to it is a one user or multiple user, it doesn't matter for the thread scheduling and all.
So SQL Server will understand that this one CPU is enough to execute this query.
That is scheduling, right? Yeah. SQL Server understand, like there are 4 threads. SQL Server doesn't matter what query that you are executing, right? It just consider that you have 4 threads. So you
Okay.
have 4 threads and I have 4 schedulers. And this 4 thread will be assigned round robin fashion. One thread
Okay.
here, one thread here, one thread here, one thread here. Even if it is a parallel execution, even one query you are executing, and this requires 4 threads to execute. And these 4 threads will be spread across 4 CPUs to execute. And SQL
Okay, for example, if we have the 6 logical CPUs,
6,
so
okay.
it will distribute to the all 6.
Sorry.
If we have 6 logical CPUs, okay, will it be spread to all 6 CPUs?
Yeah, it will spread, like see it just a 4. I have given example. Even if you have 32 or 64 CPUs, and based on the number of threads that we are we are creating at the SQL level, it will be spread across all 64 CPUs. So if you have 64, at any point of time, 64 threads can execute in a single point of time, because one thread will be spawned on the CPU and will execute. Likewise, 64 CPUs and 64 logical schedulers.
Rather than going to the 64 CPUs, SQL Server can go with one CPU and it can be executed within a little span of time.
No, because if you have only one CPU, which one you are talking about?
This one only. For example, you have a simple query. Then why SQL Server is spreading that query to all these CPUs?
No.
It has to be
You
executed
didn't
with one
understand the
CPU.
concept, right? So if you have a simple select statement, if it is not going for parallel execution, let's understand select statement is a serial execution. It is only one thread it's spawned to execute. If it has only one thread to execute, that one thread will be executing on only one CPU. This will not spawn 64 threads to execute, right? It will spawn only one thread, and that one thread will be executing on this CPU or scheduler or CPU, right? If likewise, if you are executing 4 threads, 4 SQL queries, and this each query requires one thread minimum, one thread. So these 4 queries will be spread across multiple CPUs to execute. Not individual query will spread across 64 CPUs to execute. No, each thread to execute on one CPU. If it is simple select query, which requires only one thread, that is your serial execution, that will go for single thread. If you don't have a parallelism, that we will talk later. If you don't have a parallelism at all, even if it is a huge or big query, and if we want to let it to, so go for one scheduler, one CPU, one thread, then it will be executing only on the one CPU. It will not spread across.
Okay, Chandra. Thank you, Chandra.
Right. So this is the logical. This is your logical CPUs, right? So schedulers that we call it as. Right now, the design goal, right? So we already talked control which thread should run from SQL Server. We try to run one thread per CPU, but there are exceptions, right? So there are exceptions because if you have a, so multiple, if you have a parallelism, so it will run on multiple CPUs. Priority is irrelevant, right? As far as scheduling is concerned. So we are more concerning on the scheduling, right? So how the scheduling works, each thread, it will send it to the CPU to execute with respect to whatever, I mean, so SQL, if it is SQL, all threads on the same priority, right? So there is no high priority threads which has to be sent first or not, because you have a scheduler. This is SQL scheduler. You have a SQL scheduler, then all threads in the scheduler are a SQL threads. So all are in the same priority with 7. All are in the same priority so that it will execute within the same priority. So priority is irrelevant. Not complete scheduling, just some construction to make a better decision when we use OAS to schedule our threads, right? Not complete scheduling. So it is just, so the design goal is just some construct to make a better decision. Suppose if you allow OS to schedule our threads, it is not a proper, so mechanism, right? Because the OS can schedule other threads also, or if it is a high priority threads, OS will allow high priority thread to execute. So to maintain that scheduling, we have a UMS, user mode scheduler, or we call it as a SQL operating system. Next, avoid causing a thread to switch into the kernel mode whenever possible, right? So why the other design goal is we are avoiding the context of the context switches, right? Context switch is nothing but one thread on the CPU Windows operating system executing. After 4 milliseconds, it will come out of the CPU, and the context of this current thread will be written some pointer, right? Some place it will be written, and whenever it has to thread again, the context has to be switched, right? Context switching is nothing but it has to identify where the thread execution left, and from there it executes the query, right? So that is what we see, avoiding context switches, because we are just spawning one thread at any point of time. We are not allow all the threads to execute on the CPU. Suppose asynchronous IO, that we will talk later, so it's suppose asynchronous IO when writing into the data file, right? So while writing into the data file, let's say for example, checkpoint writing into the data file, no other threads waiting, right? Asynchronous is nothing but it performs in a backend. It will not wait for that to complete. So we are not waiting anything to perform a checkpoint. Checkpoint, it asynchronously performs and writing the data pages from the cache to the memory, cache to the disk. That is asynchronous. We will talk that later when we talk about the IO performance, right? This is the main goal. Quantum, we talked already, so that time slice, a thread is given to run by a Windows scheduler, right? So it is a 4 milliseconds. So Windows creates the illusion that all threads run concurrently by partitioning the time each thread. That is what, like, so 4 milliseconds. Each thread we are allowing 4 milliseconds to execute, and it will come out of the CPU. Any questions?
I have a question.
Yeah.
So you said one thread is assigned to one CPU, right, at a time?
Correct.
So what is the configuration of the maximum worker thread configuration? The default, there is like a setting, right? Depends on the number of CPUs. So if it's like for 64-bit computer of less than 4 CPU, there will be up to 512. If it's 8, up to 576.
Correct.
And so on. So what is that configuration then?
So we'll talk that later, but to answer your question, so based on number of CPUs, let's say for example, if you have 4 CPUs and the configuration, the default configuration is, let's say 512. 512 concurrent threads can be executed. So 512 concurrent threads can be executed based on the number of CPUs that we have. So 512 max workers can be created 512. So this 512 threads, for example, let's say I have a concurrent 512 queries executed. So then 512 threads can be created concurrently, like parallelly 512 threads can be created. So all these, let's say for example, you have only 4 CPUs and all these 512 at a time it's created, all these 512 will be distributed across multiple CPUs and the behavior is same. It will allow only one thread to execute on the CPU. This is a 512 concurrent executions or concurrent threads, which can allow SQL Server to execute at the max.
So concurrent in a sense is running at the same time concurrently, right? So how we infer one at a time then, like if it's run 512 concurrently in 4 CPUs, then we divide 512 for 4 CPUs and there is some numbers, right? 100 something for each. So it can, so can we conclude that it cannot handle one thread at a time? So all the rest will be in a queue?
Correct. All will be in the queue. Yes.
So I was wondering, it looks like a conflict with the configuration. So what's the sense of like making maximum worker thread configuration on SSMS?
Maximum worker thread configuration. So you can define to set like, so more, but that will not allow, right? So concurrent threads will not helpful, right? If you have 4 CPUs, it will be like 512 threads. If you don't have any threads to create, like even if you increase that max worker thread or max worker limit to more than this, so that might not helpful, right? So all threads will be waiting on the so CPU to be available. But only one advantage by changing that value is if you reach 512, even you cannot connect to the SQL Server. So the connection will be not established because you don't have any CPU cycle to be any threads, available threads to assign the task, right? So you will see the thread exhaustion kind of thing. So if you have increased that value, so for example, 576, then the thread will be available, right? It will not, you will not have that thread exhaustion on connection failures. At least you will have the thread assigned, but it will be available. It will be waiting in the runnable queue. It will not perform any of the execution. You will see some slow performance and all. And it will not help you increasing the max worker thread limit. That is what even we don't suggest or suggest to increase the max limit, because the threads which we allow that, so the maximum, if it is reached, then it's a kind of, so stuck. Like we will have to understand what exactly running and why those threads are keep pending on the queue. Yeah. But just to answer your question, like whatever threads which are spawning and concurrently, so the concurrent threads which are spawned, so all will be in the queue and will allow, will wait for its turn to execute on the CPU.
So in this case, let's say if we have 4 CPU, we'll have like 4 schedulers, right? For 1 per CPU. So all the trends, like 100 something, will be handled by 1 scheduler.
Correct. That is true.
Okay.
That is true. That's what, right? So that is where we have that scaling up the resources, right? So for CPUs, if you have a high workload and if you are executing all at a time, so then there is a chance that, so you will see some slowness and you need some resources to be scaled up. So 512, we are giving limit just to make sure that we are establishing a connection and will, so allow SQL Server to execute whenever it gets its start. Right? So the context switches, saving information for old thread, loading information for new thread. That's what we were talking, right? So whenever a thread completes its quantum of 4 milliseconds, it will go ahead and, so it will go ahead and write that context of the thread, where the thread, what is the current information, like current execution context will be written in the pointer. And whereas it is trying to load, that context will be loaded back to the load it back and execute on the CPU. Right. So we were talking, right, a process threads, like, so I'm not going to explain again. And the process is a container which has a multiple task, which creates multiple tasks, whereas threads will assign the task and go ahead and execute that work or task, right? So go ahead and execute the thread on the CPU. So what is a thread that we already discussed? A thread is a unit of execution within the process. Multiple threads can exist within a process, right? So each is given small amount of processor time, and SQL Server uses OS threads to perform its work, right? Called a worker threads. Dedicated threads exist, like whatever, like, so most are in the pool of threads that SQL Server uses to process under request working threads, right? Scheduling. Now SQL Server has its own thread scheduling. So I was talking, right? So calling it non-preemptive scheduling and is more efficient than Windows scheduling performed by the Windows operating system layer of storage engine. So it will be performed by the Windows operating system, SQL operating system layer itself. It will not spawn to the OS. Each processor core has a scheduler. That is what we discussed. Like sys.dm_OS schedulers is the DMV to schedulers that we have. So this is basic scheduling queues that we have in each CPU. So what it is? So you have a CPU scheduler, you have a scheduler. Let's consider that you have two schedulers, scheduler 1, scheduler 2. Now each scheduler will have a different queues to handle the threads. Each scheduler will have a different queues to handle the threads. One queue is a runnable queue. Okay, whatever. So it is a old diagram, I believe. So you can consider that. You can consider this, right? So scheduling information. So this is a runnable queue. This is the waiter queue. Then another one is IO list queue. Some other, like, so timer queue, let's say. So what does it mean, right? So each scheduler will maintain a separate queue to have some scheduling. Let's say, for example, I have a thread 1. One second. So I have a thread currently executing on the CPU, right? Currently executing on the schedulers, and so like a schedule one thread, and it has to run on the CPU. Okay, so it has to run on the CPU and it is currently executing. The thread is executing on the Windows operating system scheduler CPU. Now this is a some update or select, whatever it is, and it needs some resource. It needs some resource, right? So it needs some kind of take lock. It needs lock, or it requires some page, right? It needs some page IO latch. Let's say, for example, page IO, whatever, lock, thread, pull, some so backup IO, anything like it is waiting for some IO request. It needs some IO. Then the thread cannot be keep running on the CPU to wait for a resource, right? So that is where we see if a query is running slow. If the query is running slow, main thing we need to understand whether the query is running query or waiting query. The reason, if a query is waiting, then the CPU will not take, CPU cycle will not take. If the query is running, then it is not waiting for any resources, right? So if the query is waiting for some, it needs some resources, it will not wait for CPU. It will not wait on the CPU. It will not keep executing on the CPU, and it will not wait for some resources, right? It will come out of the CPU to the SQL scheduler, let's say. It will come out of CPU and it will be, so go back to the SQL scheduler and put it on the waiter queue. The thread one needs some lock and it will be in the waiter queue. The same thing, IO list, it needs some IO operations. Let's say, for example, it has to write into the into the, for example, it has to flush the pages, or it has to write something, or it has to fetch something, some IO information. It will be written to the IO list. So where is that IO request? Let's say, for example, we are doing some IO, right? Input output. So if we are doing any IO request, that will be also waiting in one queue. So where that will be waiting, that has its own IO queue, IO list. It will be waiting on this thread. So some processing asynchronous IO, right? Some, let's say, for example, some internal process or some threads which is processing an IO request, right? It posted an IO. So if it is posted an IO, the thread not keep on running on the so CPU, right? It will come out of the CPU and it will be placed in the IO list. As soon as the IO process is completed, then it will go back and execute on the CPU. I will talk that. But if it is waiting for some IO to process, or the current IO request is progressing, then it will be placed in the IO list, IO queue. And timer queue. Timer queue, let's say, for example, I have some scheduling threads. Let's say, for example, checkpoint execution every 1 minute, right? So checkpoint execution every 1 minute. At the same time, lazy writer in a specific period of time. Resource monitor, right? Resource monitor thread. This is also one thread. So resource monitor, it will check if there is any issues with the memory or any resources. So it will trigger accordingly. But resource monitor, scheduler monitor, that will be a schedule, that will be in a time slash, like for example 5 seconds. Resource monitor and all executes 5 seconds to see if there is any so CPU memory basically. And scheduler monitor, scheduler monitor thread, right? It will check if the threads are scheduling properly or not. It will check for every 5 seconds. So those threads will be in the timer queue, right? It will be in the timer queue, timer list. Now, so I was talking this thread, waiter, IO, and timer. So what is this runnable queue? Runnable queue is a thread which is not waiting for any of the resources, or is not in the any process, so it is not waiting for any resources. So whatever resources which it requires, all it has, and it is ready to be running on the CPU. So runnable queue is nothing but it has its own, it has all the resources it requires to run and waiting for CPU to be available, right? So I need CPU cycle to be available. Go ahead and execute on the CPU so that you will have all the threads waiting on the runnable queue. So runnable queue is when the thread is executing. I mean, when the thread is ready to execute on the CPU, you will have that thread in the runnable queue, right? Runnable queue, a list of processes that are ready to run on the CPU. So waiter list, a list of processes that are waiting for some resources, right? It can be anything, lock, it can be backup IO, it can be some wait types that we have. We will talk that later. Like if it is waiting for any resource, let's say for example, it is waiting for some memory resource semaphore. So if it is waiting for HDR sync command, right? So whatever it is waiting for, it will go out of CPU and it will keep it in the particular list, that is waiter list. So work queue, a list of processes that are required to give in a scheduler and are waiting to served by a active worker thread. So this is, I will talk that. And timer, so this is waiting for some lock monitor or whatever, you know, so timer list, like whatever scheduling frequency, let's say resource monitor thread, it has to execute on an interval, right? 5 seconds or checkpoint 1 minute. So everything will be in the timer list. IO request is some IO, you know, so request has to be processed, that will be in the IO request list. This is how the request works. The runnable queue, this is a FIFO. Now let's understand. A thread currently executing. So any questions on this? I'll clear. Okay. So this is your scheduler one, let's say. So I have a CPU. CPU one. Now a thread, I have 4 threads here, let's say in the queue. So where these threads will be available, ready to be running on the CPU, these threads will be in the runnable queue. These all threads will be in the runnable queue. One thread from the runnable queue, the header are first in the queue. Let's say this is your runnable queue and you have thread 1, thread 2 and thread 3. Right? So this will go ahead and execute on the CPU. The remaining 2 threads will be in the runnable queue of that particular scheduler. Each scheduler will have its own queues, right? It will be in the runnable queue. Then if it is about to come, if the thread is completed its execution or is require some you know, so resources, or it has to come out of the CPU to go back to the SQL operating system, then it will be signal the you know, so to the next thread that I'm coming from the out of CPU, then you can schedule the next thread, right? It will be giving signal to the scheduler, the current executing thread, it will give a signal to the scheduler, and the next thread in the scheduler will go ahead and execute, right? So the thread which is coming out of CPU, it will give a signal to the thread which is there in the runnable list, and the next thread will be scheduling. That is what we call it as a cooperative schedulers. Cooperating is nothing but it just tell that I'm coming out of CPU and the next thread has to be executed. Right, whatever threads which are coming in, it will tell that the thread I have done my work and I'm coming out of CPU, and the next thread has to be spawn and execute on the CPU, right? If this thread you know, okay, so that is what we call it as a cooperating, right? So it has to come out of CPU and it will be placed in the runnable queue. For example, we'll talk that in a bit. That is a runnable queue. Now let's understand that I was talking about few lists, right? Each scheduler will have one of these lists: runnable queue, IO list, that is your IO task, IO pending, like write IO or IO completion or IO asynchronous IO or backup IO, whatever it is, like it is in the IO list. The thread will be in the IO list. and timer list. That is what we were talking about: checkpoint thread, lazy writer thread, scheduler monitor thread, or resource monitor thread, right? So you'll have the timer list. Waiter list, if the query is waiting for some resources, right? Like some lock, some blocking, some memory, resource semaphore, it is waiting for some memory to be compiled, right? So high availability. So all threads waiting for some resources will be in the waiter list, right? So now you see here, I have a runnable queue. I have 3 threads in the runnable queue, right? So 3 threads waiting. So I have different queues I have. Now let's say one thread is currently executing on the CPU. That is what you see here. One thread is currently executing. Now this thread is coming out of CPU, right? If the thread is coming out of CPU, then it will go back to the runnable queue at the end of runnable queue, right? So if the thread is coming out of CPU, let's say it met quantum, or it's not quantum, it met some yield point and it is coming out of CPU. If it is coming out of CPU, then it will be placed in the end of runnable queue. The thread which is scheduling, which will be in the runnable queue, is in a first in first out basis, right? So whatever threads which is coming in for the first, it will be in the header of the queue. Remaining or will be in the tail of the queue, right? The thread currently executing on the CPU, it is coming out of CPU for whatever reason. It is coming out of CPU and it is going back to the runnable queue. In the first thread, which is in the waiting list, so which is in the runnable queue, we'll go ahead and execute the thread. Now let's say the thread, some other thread is waiting on the resources, some resources. One thread is waiting for some resources. If it is waiting for some lock, let's say it is waiting for some lock, this lock, it got the resource, right? If it get the resource, then it has to execute on the CPU. Then how this execution happens, it will not directly go and execute on the CPU. It has to be placed in the runnable queue. Let's see. Okay, whatever, right? So this is the IO list. So it is waiting for some IO operation to be completed. As soon as the IO operation is completed, then this IO thread will go ahead and placed in the end of the runnable queue. So it will be placed in the end of runnable queue because, as I said, these are all in the same priority. So there is no priority driven, so that whatever threads that we have, it will go ahead and place it in the runnable queue, end of the runnable queue, and waiting for CPU to be available, right? So as soon as it is completed its IO request, it will be placed in the end of the runnable queue. And if waiting is completed, then it will be placed in the, sorry, whatever, like there is no so kind of priority or whatever, that just timer list, for example, it will be at the end of the runnable queue. At the same time, if it is a waiter, if it receives that waiting whatever resource it requests waiting for, then it will be placed in the end of runnable queue to execute further, right? So the worker pool, right? So you need a task, you have created a task and it needs some worker, then the worker will be assigned from the worker pool of individual schedulers. This is for the individual schedulers that we have, right? So the task is created and assigned to a worker from the worker pool of the individual schedulers that we have. This is just a high level, the same thing. I have no thread and no CPU, right? So if I don't have a thread, if I don't have a thread and don't have a CPUs to run, then it will be a pending. So because you don't have a thread to assign a task, it has to be waiting or pending for the task to be assigned to a thread. But I don't have a thread because I have exhausted my number of threads the SQL server can assign. Now it is in the runnable queue. So what is runnable queue that we talked? So I have a thread, but no CPU. So CPU cycle is not available. So it is waiting for CPU to be available. I have a thread and CPU. It is executing on the it is executing on the CPU, right? I have a thread and I have a CPU. Now I don't have a CPU. I mean, I'm waiting for some resources, anything, right? Any lock or anything. That is what that is where we see waiting. The status is suspended, right? So I am doing nothing, right? I'm doing nothing. So I have completed my execution. I am doing the session is open. Then we see that status as sleeping, right? These are all you will see in the sys.sys processes or sys.dm exec request except sleeping. The DMV that we have. So handling work request. This is so the handling work request. This is just a high level. So you have an incoming work request and it checks whether the idle worker available or not. Worker is nothing but an idle thread is available or not. So if a thread is available, then assign the request to the worker. Then assign that request to the thread or worker, and it will be placed in the runnable queue. Right, it will be placed in the runnable queue and it will wait for CPU to be available and it executes on the CPU, right, from the runnable queue. If idle worker is not available, then worker limit reached. So we'll have to check worker limit is reached or not. If the worker limit is reached, then work request queue. It will be in the work request queue so that it will be waiting for a worker to be available. Worker is a Windows terminology. We call our SQL terminology is a thread. So we'll have to wait for thread to be available. So if a worker limit is not reached, right? So, but you don't have a idle worker available, then it will create some worker and will assign that request to that particular worker to proceed your execution. Then again, that will be placed in the runnable queue and waiting for CPU to be available. This is just a high level, process how the task will be assigned and executed on the CPU. Okay, so any questions? That is how the scheduling and so the scheduling and SQL OS takes care of that execution. And if you notice, if the thread is waiting on this runnable queue, that is where you see that SOS scheduler yield. So you might observe that SOS scheduler yield wait. That is what it is waiting SQL OS to schedule and waiting for the thread to be yielded. That is what you notice, that SOS scheduler yield, the thread which is there in the runnable queue. And you'll have to notice two things. One is the time it is waiting, and second thing is we'll have to notice the signal wait time, right? Whenever you execute, select start from sys.dm_os wait stats, right? We will talk this more when we're talking about the weights, right? So if you see that signal wait time in milliseconds, that is what it is waiting for the signal to be given, right? So what does it mean? The thread which is currently running on the CPU will give a signal to the next thread to execute on the CPU, right? So it will tell how much time this thread is waiting for signal, right? If it is waiting for a longer signal, then it means that the query is currently running very long on the CPU, right? Until then, you will see that SOS scheduler wait time, right? So I'll stop here. Any questions?
Question.
Mhm.
So let's say if we have an issue, performance issue. So which are the things that we look from here?
So if it is a performance issue, so we'll have to check first thing whether the query is a running or waiting query. If it is a running query, so we'll have to see if the query is running for longer. If it is a waiting query, then we'll have to see if the query is waiting for any of the resources. Either it is a runnable SOS scheduler, what wait type, and we'll have to check from there, right? So either it is a SOS scheduler yield, then we can consider that it is not waiting for any resources. It is waiting for CPU to be available. Or if it is waiting for some wait resources. So you will have to check the wait time and signal wait time also from this diagram that you are talking. Like suppose if you need anything, so signal wait time also. Signal wait time, it tells how much time the thread is waiting to get a signal from the thread which is currently executing on the CPU. So that signal wait time, you will have that in the 6.em_os wait task DMV.
What if there is a lock? Like, let's say that if there is a lock
Lock, okay.
on one of the locking, if there is locking in one of the resource, and it's like which one is applicable area for that? Will it be on that will if it will be on a running one, right? If there is a locking or blocking, what's gonna
It is
happen
a
to that?
lock, latch, blocking, whatever it is, it has to wait for some resources. If it has to wait for some resource, let's say for when we wait for lock or there is a blocking. So when we wait for a lock, because the resource, it is already acquired a lock. I mean, some other process is taking that resources, using that resources, and this query or this thread has to wait for that resource to be available. If it has to wait, then it will be not waiting on the CPU. If it is waiting, the wait time is not estimated, right? The wait time can be 1 minute or 1 hour, 1 hour. It cannot keep running on the CPU. If that is keep running, then other thread will be blocked. Other thread will not have that cycle to execute on the CPU. Then it will come out of the CPU and it will be placed in the waiter list. Once the resource is acquired, once the lock is acquired, then it will go ahead and execute on the CPU. Now it will be in the runnable queue and it will wait for CPU to be available. That is the reason whenever you see blocking, then we no need to troubleshoot high CPU utilization, right? Whenever you have high CPU utilization, you no need to troubleshoot blocking. You'll have to check what are all threads which are currently executing on the CPU and taking more CPU. If it is waiting, that is not running. If it is running, that is not waiting for some resources.
So that's great. Can you touch one more time that SOS scheduler yielding?
Yes.
What's
You
that?
want me to
Can you like simplify one more time?
Sure. So SOS is nothing but SQL operating system. So we have a scheduling mechanism at the SQL operating system. We have our own scheduling. So what it meant to be, so the thread which is not waiting for any resources, so it is not waiting for any resources, or it is not IO list or anything. The threads in the runnable queue, the threads which are available in the runnable queue, and the threads which are in the runnable queue waiting for the thread which is currently executing on the CPU and waiting for this thread to be yielded. So yielding is nothing but, here in this context, yielding is nothing but come out of CPU and go back to the SQL operating system scheduler. So the thread is waiting for CPU to be available. So in a simple words, the thread in the runnable queue is waiting for CPU to be available to execute. It is not waiting for any resources. It is just waiting for CPU to be available so that the thread will go ahead and execute on the CPU.
So from the system OS wait, are we able to like estimate how long it will wait on the runnable queue?
Correct. Yes. So we can see that, so timer, this is sys.dm_os stats. This is a historical information since we restart the SQL instance. Since we restart the SQL instance, we can find sys.dm_os waits. So if you want to aggregate or consolidated information, so how long it is the thread is waiting for whatever resources that we have, and you can see sys.dm_os stats. So this is the wait time. This is the maximum wait time. But here, if you see that signal wait time, this is what I was talking, right? Signal wait time, based on the signal wait time, we define whether this thread is waiting more time to get the response or not. Signal wait time is nothing but this thread, how long it is waiting to get a signal from the thread which is currently executing. Let's say this is 100 milliseconds. If it is 100 milliseconds, then it will be waiting for 100 milliseconds to get the resource, to get the so signal from the thread which is currently running. If it receives the signal in 1 milliseconds, then it is considered as a 1 millisecond, then it is fine. If it is waiting for long, then it is considered as it is some CPU bound query executing and it is running long. So the other DMV that we have, sys.dm underscore OS underscore sys.dm underscore OS underscore waiting tasks. It also gives valid information like whatever the session which is waiting, context, resource address, blocking information, that all, right? So you will have that. This is the current executing task. This is the historical information, but you'll have to identify if there is any waits which has more signal wait time. Suppose if it is SOS scheduler yield, then it is we'll have to check what is the signal time it is waiting for. But yeah, so we will talk that more in detail, like when we talk about the wait times.
Right.
Cool. So any questions?
Hello.
Sorry.
Hello, Chandu.
Yep. Ayan.
Yeah, yeah. Actually, that is the main thing. Which parameter need to check if you are getting the CPU.
No, I
getting confusion in that.
what is that?
What need to check if you have CPU? What need to check?
Sayan, your voice is completely low. I cannot hear you.
Now I'm audible.
Yeah, tell me.
Yeah, a little bit getting confused that if you are getting any CPU issue, memory issue, buffer cache hit issue. So correctly, what parameters need to check that I need to learn. Sometimes if we are getting CPU, we are checking everything that blocking, the deadlocks, everything. So exactly we need the parameters. What we need to check.
So you will have to, I mean, so definitely that we will discuss, but not in the, so it's a performance tuning, it's a way to go, right? Like it is not simple that have one parameter to, so and track the some issue, right? So you will have to investigate the issues. For example, there is this long running query. So if it is a long running query, then there is no point that you will have to first long running query, then you'll have to understand if it is a waiting query or running query. So from there, you'll have to check whether the query is waiting for, I mean, waiting or the query is running, you will understand. So let's say if there is no specific query, the complete application is slow, for example. If that is the case, there is no point of reviewing individual queries, right? So you'll have to check the complete server level performance. So then either any memory or any CPU or anything. So if you're asking is parameters, we will talk that later, but we don't have any specific one place, so everything to check, but just a high level, you have that SQL server and here like a report where we have the performance dashboard, where we can see the high level report, right? So like what is the current the resources or wait type or whatever it is, you will see that high level to understand what is the utilization of the system, current wait requests, and so you will have that wait types and all. If you click here, then it will go further down and understand what it is waiting for. This is a useful so information that you can look at the initial understanding and so investigation. But yeah, definitely I don't have a straight answer to you. Like if it is a performance, then you'll have to spend more time to understand the issue and troubleshoot that. But before you even go for troubleshooting, my personal experience is to ask more questions, right? So I came across like a performance issues. So we don't know what is the performance issues, right? So application team says that it is a performance issues. So if you ask more questions, like when that happens and since when they started seeing this issue, or was that there was any changes or any specific query they noticed, or any specific process or any errors or any execution slowness or anything that they noticed, then from there we will start working on that, and we'll so reduce our investigation time if you ask more questions, so that it will help us to find the issue properly. But we will talk that, like we will take some scenarios and we'll talk. Maybe not all the scenarios, but at least I can help you where to start and how to investigate the performance issues.
Yeah, most probably the application team will blame on DBS only. So at
That
that
is obvious,
time,
like, if you are DBA, that is obvious that they'll blame us. So that is where, like, we will have to prove that either it is a SQL issue or not.
yeah. Is there any particular query, Chandu, that we can say that the issue is from application team?
No, that we cannot tell, right? So what we can check, so we'll see that whether there is any long running queries, or whether there are any CPU bound queries, or any CPU intensive queries, IO intensive queries, memory. So anything which is related to queries, that is something that we can tell that this is these are all queries which are running and taking more resources. The fine tuning of the queries, again, that is application team task, that they'll have to fine tune, either changing data type or changing parameters, or avoid implicit conversions, or any avoiding fine tuning the query, that they'll have to check. But we cannot run simple any query and tell that this is not a SQL issue, right? So only thing you'll have to check whether any SQL intensive operations are running. So if that is the case, we will say that it is some CPU intensive queries running, and we'll have to take care of that.
Okay, Chandu, for every troubleshooting, we have documentation for this.
Every troubleshooting documentation as in?
Yeah, like CPU, if we have issue with the CPU, memory, like this.
Yeah. So I'll explain, like I can provide you, so the scripts to investigate, and I can create, I have a Git repo so that I can share that scripts, so that you can use those scripts, so to while troubleshooting the issue.
Okay. Thank you, Chandu.
So any questions? I think it is 10 minutes late. Yeah.
Not a question, but where can we find the recorded videos?
Recorded videos, we will share. I believe that Shanmugh has already shared the recording videos, but if not, I'll let him, to share those recording videos to you. Like, I don't know who is the point of contact, but I will so share that. We'll ask him to share that recording videos.
Okay, thank you.
Please, can you share the second wait time again? Is it sys.dm_os_waiting_task? Yes. Okay. Thank you. I've seen what.
So you're asking this way.
Yes.
Okay.
Yes.
Is the DM_OS waiting task. That is the current waiting, so that current task which is currently executing. And this will have the historical information since the SQL is started.
Okay.
So I know we have to follow different procedures, based on the issue, right, for performance. If you have like a documentation where to start and of the script of repository, and if you'll be able to share with us, that would be great.
Definitely, yeah, definitely. But I will not share that before. But so after our class, maybe that will make more sense to have that, so details or the scripts, whatever we have.
Sure.
Definitely, I will share. Cool. Okay, I'll stop here. If you don't have any questions, we'll go drop, and then we'll connect next time.